Inside the most complex manufacturing tool on Earth, a high-powered laser fires tens of thousands of times per second. It strikes microscopic droplets of molten tin, turning them into plasma that emits extreme ultraviolet light. This extreme ultraviolet, or EUV light, is bounced through perfectly smooth mirrors to print patterns onto silicon smaller than a single virus. Only one company in the world builds the machines capable of doing this, ASML, based in the Netherlands. They hold the absolute choke point for the global semiconductor industry. For 60 years, the global economy has run on a simple mathematical engine known as Moore's Law. Shrink the transistor, pack more of them onto a chip, and extract more computing power at lower costs. Today, maintaining that physical scaling at the leading edge strictly requires EUV technology. In 2019, the United States enacted severe export controls against Huawei. Following diplomatic pressure, the Dutch government withheld export licenses, ensuring ASML would not deliver its most advanced machinery to Chinese foundries. Without those machines, the established path for shrinking silicon was cut off. Reaching the leading edge of computing through conventional physics became economically and practically impossible for Huawei. Cut off from the frontier, Huawei turned to domestic foundries. Their engineers took older, less advanced lithography tools and pushed them far beyond what they were originally designed to do. They relied on a technique called multi-patterning. Instead of printing one incredibly dense circuit pattern in a single flash of light, the foundry splits it into several simpler patterns. You print the first layer, etch the silicon, and then repeat the process for the next layer, stacking them together. The mathematics of this approach are brutal. Every time a pattern is split, the number of exposures on a critical layer doubles. Each pass has to align with the previous one with nanometer precision. A single defect on layer 1 amplifies across the subsequent passes, sending manufacturing costs and production times skyrocketing. Through sheer force of capital, Chinese foundries managed to use this method to produce 7-nanometer chips. But that is the physical ceiling. Below 7 nanometers, the error rates multiply so rapidly that the economics of multi-patterning completely collapse. Walled off from the tools required for conventional progress, Huawei had exhausted its options for shrinking transistors. To stay in the semiconductor race, they had to abandon Moore's Law entirely and find a completely different metric to optimize. After 7 years out of the public eye, the president of Huawei semiconductor business, He Tingbo, returned to the stage in Shanghai with a surprising diagnosis. The entire industry was measuring the wrong variable. When you look at the physical layout of a modern processor, it resembles a massive, dense city connected by a network of tiny metal highways stacked up to 20 layers deep. The primary limitation of this system is no longer how fast the logic gates can switch. It is the physical distance the data has to travel between them. Engineers call this RC delay. Every signal traveling across those metal wires encounters physical resistance, slowing it down. Simultaneously, every wire acts like a tiny parasitic battery, draining energy to charge and discharge every single time information moves. The longer the trip, the slower and hotter the system becomes. This chart shows the distribution of energy consumption in large-scale AI clusters. According to Huawei's internal analysis, more than 80% of a massive computing cluster's power is spent strictly on moving data across these pathways, rather than actually computing anything. The processors are spending their energy playing messenger. The true bottleneck in modern computing is the physical commute. To solve this, Huawei proposed a concept they call tau scaling. Instead of measuring progress by shrinking nanometers on a physical axis, they are measuring progress in nanoseconds, optimizing the time it takes for data to clear the critical path. The architecture designed to execute this is called logic folding. The concept works exactly like folding a sheet of paper in half. Logic that was previously spread wide across a single flat piece of silicon is split across 2 separate layers, placed face-to-face and stacked. Components that used to sit millimeters apart on a flat plane now sit directly on top of each other. Signals that once had to crawl horizontally across the die now make a microscopic vertical jump. The journey shrinks by a factor of 10 to 100, and the resistance drops with it. Bringing those layers together relies on a manufacturing process known as hybrid bonding. Rather than using traditional solder bumps to connect finished chips, The foundries fuse two raw silicon wafers directly together, copper pad to copper pad. Huawei claims they can achieve a bonding pitch, the distance between these vertical connections, of 1.5 microns. That creates a connection grid roughly 6 times finer than the best 3D packages shipping in Western processors today. At a 1.5 micron pitch, the interface between the wafers effectively disappears. The connection density is so high that the two distinct layers stop acting like separate chips communicating with each other and begin functioning as a single continuous circuit. By vertically stacking components built on their older 7nm process, Huawei claims they can achieve transistor densities equivalent to a 1.4 nanometer node. They are attempting to bypass the geopolitical restrictions on ASML machines by moving their architecture into the third dimension. But navigating around a geopolitical wall simply puts them on a collision course with the laws of thermodynamics. The industry has successfully stacked memory chips for years, but memory is mostly passive. It sits quietly and holds data. Logic chips switch billions of times a second, releasing intense bursts of heat. When you fold two active logic layers face to face, the heat generated by the bottom layer is trapped directly beneath the top layer. Huawei's first target for this folded architecture is not a server rack with liquid cooling lines and giant heat exchangers. Their target is a smartphone processor, a device with no fans, relying on a thin sheet of graphite, operating while resting against a human hand. A processor that cannot shed heat cannot sustain performance. If materials engineers cannot invent a way to extract the thermal load from the center of that silicon sandwich, the logic folding architecture will melt before it reaches mass production. Looking strictly at the silicon, the leading global foundries remain far ahead. TSMC has 2nm chips entering volume production and has already demonstrated heavy yields on their own future generation nodes. Furthermore, the shift in focus from transistor size to data commute is exactly where the rest of the industry is already heading. Companies like NVIDIA and AMD are heavily invested in advanced packaging and 3D stacking to manage data movement across their processors. The lasting impact of Huawei's strategy isn't tied to the success of one specific processor in 2026. The real concern for international regulators is the parallel supply chain assembling behind it. Chinese toolmakers and universities are actively building the domestic bonding equipment and design software required to execute these 3D architectures completely in-house. By severing access to off-the-shelf global tools, the restrictions force domestic engineers to rethink chip design from first principles. The export controls were designed to halt the advancement of China's semiconductor industry. Instead, they forced the creation of an entirely separate ecosystem. Blocking the conventional path did not stop the progression. It simply forced the development of a different route up the mountain.